Good day everyone and welcome to our next lesson. In this video, I will be discussing about chemical thermodynamics. So this will be a two-part lecture. For this part, we will be focusing with the basics of chemical thermodynamics and we will be laying down some important principles and we will be discussing calorimetry as well. So let's begin. Our perception and understanding of energy will be very important in our study of thermochemistry because this entire topic revolves around the transfer and transformation of energy. Let's first explore what energy is. We define energy as a physical quantity that has the capacity to do work or that has the capacity to heat an object. Energy can also be defined as a quantity that can be transferred and transformed while being conserved in the process. By this point, we know quite a bit about energy. Energy manifests physically around us every day and it is observable, such as the heat coming from the sun, that is radiant energy being transferred. Energy also manifests itself during combustion reaction, so when you are burning something. And you can also observe energy in action when you are using your gadgets, your phones, your laptops, etc. Those applications all fit the definition of energy. However, they exist in different forms. Some common forms that we are encountering include thermal energy in the form of heat. We have work. We can also have potential energy, kinetic energy, electrical energy, and so on and so forth. For our discussion of chemical thermodynamics, we will mostly be dealing with chemical potential energy and heat. That is what is pictured in this example here. So in the tweezers, we have a little pellet of sugar or sucrose, and in the heated test tube, we have some potassium chlorate. The potassium chlorate is a very strong oxidizing agent, and what it does is it has the capacity to release the stored energy of some compounds. So when we drop a pellet of sugar onto the heated potassium chlorate, what happens is that the sucrose gets oxidized and its oxidation releases a lot of energy. So this is a visible release of chemical potential energy. Next, let's talk about units of energy. So what units can we use in order for us to quantify the amount of energy being transferred or transformed? We are using joules for the SI system. In the English system of units, we are using BTU or British Thermal Units. And we can also use the unit of calorie. Now we can use kilocalorie, kilojoules, megajoules, etc. So you can use prefixes in order to reflect the magnitude of the energy. Now speaking of transformations of energy, our previous example is a prime illustration of the transformation of energy. Again, it's from chemical potential energy to thermal energy. However, in the natural world, the transformation of energy is not just limited to one type. In fact, there are countless examples that we can name that demonstrates a transformation of energy. So say for example, for falling objects, that is a transformation from potential energy to kinetic energy. For power generating turbines, we have the transformation from kinetic or mechanical energy to electrical energy, and so on and so forth. Now, let's define the first law of thermodynamics. This is the most important principle that will guide us into our entire study of chemical thermodynamics. So what is the statement of the first law of thermodynamics? It's a very easy statement. It just states that energy cannot be created nor destroyed. It can only be transformed from one form to the other, and it is totally conserved. Totally conserved meaning the total energy input should be equal to the total energy output. So you cannot destroy energy, and you cannot create energy out of the blue. You can only convert energy from one of its forms to another one of its many forms. And with all of those changes, energy is always conserved. So do not forget the first law of thermodynamics. The concept of the first law of thermodynamics will be useful for us later in calorimetry in order for us to draw up mathematical relationships between the heats that are being absorbed and are being released. The core concept of chemical thermodynamics lies upon the amount of energy that is being absorbed or is being released by chemical reactions, because that is what we are concerned about here. So we have here two types of reactions. One is endothermic and the other is exothermic. Now, the classification if a process or if a reaction is endothermic or exothermic lies upon where is the heat involved. Is the heat being released part of the product, or is the heat being absorbed and is part of the reactants? Take a look at the first equation. For the first equation, we have the combustion of methane. So that is methane plus oxygen yields carbon dioxide plus water. However, in your product, we have an additional of plus 890 kilojoules. So this is your heat term. That means that this amount of heat is being released by the process. How can I say that this is being released by the process? That's because the 890 kilojoule term is part of the product, meaning the release of heat is one of your products. This is what we call an exothermic reaction. Exo meaning outside and thermic meaning thermal energy. So it basically means the release of thermal energy. Okay? For our second process here, this is not really a chemical reaction, rather a physical process wherein solid water or ice transforms to liquid water. Now, if you take a look at this term here, the 6.02 kilojoules, this heat term is not part of the product. It's actually part of the reactants. So we interpret that as we need 6.02 kilojoules of energy to be absorbed by ice such that it will be able to melt to water. So in this case, the heat is not being released, rather the heat is being absorbed. And we call this processes as endothermic. Endo meaning inside or within inside, and then thermic meaning thermal energy. It literally means the absorption of thermal energy or thermal energy that is going in. Okay? So do not forget our classification of exothermic and endothermic. Next, let's discuss a little bit about activation energy. So even though we will not be dwelling much about the concept of activation energy, it's important that you know what is an activation energy. So if we take our previous example, the combustion of methane, our reactants in that example are methane and oxygen, and our products are carbon dioxide and water. If you take a look at the potential energy of your reactants, methane and oxygen, it exists at this high level. And if you compare that with the product, we can say that the potential energy of the reactants is greater than the potential energy of the products, meaning that there is stored potential energy in your reactants that is waiting to be released. And if that stored potential energy is released, your products would then be at a lower potential energy, meaning some of the stored potential energy of the reactants were released during the process of the reaction. Now, if we take the difference between the potential energies of the reactants and the products, you see here that the difference equates to the amount of heat that is evolved in the process of the reaction. So if we go back to our previous example, the heat being released in the reaction is 890 kilojoules. And if you take a look at the activation energy diagram, the difference between the potential energy of the reactant and the product is also the amount of heat being evolved. Okay? Now, the other thing that we notice in this process is there is a peak or there is a maximum points in the curve. Now, notice that this maximum point of the curve is greater than the potential energy of the reactants and the products. We call this the activation energy. If we subtract the potential energy at the peak and the potential energy of your reactants, this shows that we need to supply some energy before the reaction can start to happen. Without the activation energy, there is no way for us to cross from the reactants to the products because we have to cross this mountain. So you can think of this as a roller coaster. At the beginning, you start at the level of the reactants. Now, for you to be able to climb the mountain of the roller coaster, you need to supply energy to the cart such that it can be transported from this low level up to the peak point of the mountain. Once the cart of the roller coaster starts to slide beyond the peak of the mountain, then the cart of the roller coaster will just rely on gravity to simply slide down into the level of the products. So it needs a little helping hand at the start of the process, but once we have crossed the maximum, then the reaction proceeds without intervention. A very good example of a chemical reaction that needs activation energy is a combustion reaction. So let's say, for example, that you have a piece of paper and you want to burn the piece of paper. That piece of paper will not burn on its own, even though oxygen is naturally present in our atmosphere. So in order for the paper to burn, you have to supply it with an initial amount of energy. And that's the purpose of ignition. You need to ignite your fuel first before it can start to burn naturally. Okay? So always remember this concept of activation energy. Next concept is enthalpy. You need to be familiar with the concept of enthalpy because this will be heavily used in the second part of this lecture. The change in enthalpy, or delta H, is the quantity of heat absorbed or released for a given process at a constant pressure. So for all of our examples, once the problem has mentioned that heat is being absorbed or is being released, it is pertaining to enthalpy. We denote enthalpy with the symbol capital H, and enthalpy is a state function. State functions are very special in the fact that you only need the initial and final values of the state function for you to be able to know the change in the system. So let's say, for example, for enthalpy, if you want to know the change in enthalpy of a system, you only need to know its final and initial states. You subtract those, and then you get the change in enthalpy. Okay? This formula does not work for all properties or for all parameters. It only works for state functions. Other examples of state functions include temperature, volume, internal energy, and entropy. Now, let me illustrate some very important aspects of thermodynamics. Okay, let's circle back to the first law of thermodynamics. Mathematically speaking, the first law of thermodynamics can be described by the equation delta U is equal to Q plus W. Delta U is what we call the change in internal energy. Q is heat transfer, and W is the rate of transfer of work. So this equivalency of the first law of thermodynamics states that the total change in the internal energy of a system is dependent on how much heat is absorbed or is lost by the process and how much work is being done by or to the system. I have discussed earlier the concept of enthalpy, but where is the enthalpy in this equation? The enthalpy is actually hidden in the internal energy. So our equation that transforms enthalpy to internal energy is H is equal to U plus PV. Now, P and V refers to pressure and volume respectively. And if our system is not a gas, meaning that even large changes in pressure will not likely affect its volume, we can cancel this PV term and we can say that your change in enthalpy is equal to your change in internal energy for some systems only, mainly for non-gaseous systems. So if this is the case, we can now say that the first law of thermodynamics simplifies to delta H is equal to Q plus W. Now, for specific processes wherein there is no work, remember, we will only have work involved in our first law of thermodynamics if your system is either expanding or contracting. Because the work that is included in our expression here is what we call expansion work. So if your system is non-gaseous, let's say for example it's a liquid or it's a solid, then we can almost always assume that work is zero for that process. That's why at constant pressure, we have the relationship delta H is equal to Q. That means that the change in enthalpy of the system is equal to the transfer of heat to and from the system. Always remember this equivalency. And then we can solve for delta H or we can solve for Q by the equation M Cp delta T, wherein M is the mass of the substance, Cp is what we call the heat capacity, and then delta T is the change in temperature. So basing from this equation, the change in enthalpy of the system is directly proportional to the change in temperature. So if there's a large change in the temperature of a system, we could also expect that there is a large change in the enthalpy. Or in other words, if there's a big change in temperature, we can also expect that there is a big exchange of heat. We have two signs of heat. We have the positive and the negative. And it's very important for you to discern when are you going to use the positive sign and when are you going to use the negative sign, because that will ultimately affect our calculations. The question now is, how do we discern if we're going to use a positive sign for Q or a negative sign for Q? Because sometimes in problems, it will not specify if your heat is positive or negative. I will be discussing both heat and work in this case. For our entire study of thermochemistry, it is very important that you define what your system is. Your system is usually the object that you are pertaining to in the problem, or the system is the object that we are most interested in. Let's say, for example, you want to know how much energy will be involved if you are heating a cup of water. So in that case, our system is the cup of water because that is what we are interested in. And everything else outside the cup of water is called the surroundings. So if there is heat and work involved, both heat and work will be exchanged from the system to the surroundings and vice versa. So if the flow of heat is coming from the surroundings to the system, meaning it's going into the system, we say that the heat in that case is positive. We can also say that the system is absorbing heat from the surroundings. And it is at this case wherein we call the process endothermic. Okay? Always remember, it's endothermic if the Q or delta H is positive and if the flow of heat is from the surroundings to the system. So it's going into the system. Now, the opposite, if heat is being emitted by the system or heat is leaving the system or heat is being expelled by the system, this is the case wherein our Q has a negative sign and the process is called exothermic. Okay, so don't forget, exothermic, negative Q or negative delta H, and heat is going out of the system. Endothermic, Q or delta H, both positive, and heat is going into the system. Now, how about work? If work is being done by the surroundings to the system, meaning the surrounding is exerting force into the system such that it causes work, that work would then be positive. And the opposite wherein the system is exerting work to the surrounding, meaning the flow of work is from the system to the surroundings, that work is negative. So for both heat and work, if it's coming in, then that's positive. And if it's going out of the system, then that is negative. Okay? We will be applying this concept in our future examples. Going back. Now, let's talk about calorimetry. This will be the highlight of this lesson. Calorimetry is one of the methods employed to measure the amount of heat released or absorbed during a chemical reaction. So this is an example of a coffee cup calorimeter. It's called a coffee cup calorimeter because the vessel that we are using here are styrofoam cups or polystyrene cups. So it just looks like a cup of coffee. Now, the reason why we are using polystyrene cups is that they are a very good insulator of heat, meaning if heat is being transferred inside, then very, very little heat is going out of the process. Okay, so for our coffee cup calorimeter here, normally a chemical reaction will be happening inside, either a chemical reaction or a physical change. And then we have here a thermometer that records the change in temperature during the chemical reaction or during the physical process. The change in temperature, whether it is from high to low temperature or from low to high temperature, dictates how much heat is being released or is being absorbed by the process inside. Okay? So for our purposes, we are calling this an isolated system. It's an isolated system because neither energy nor mass can go out or go in our system. For the calculations involving calorimetry, we need to perform heat or energy balances. So let's try to perform the energy balance for a coffee cup calorimeter. One of the good things about coffee cup calorimeters is that they are very easy to construct and they are very easy to source. And another advantage of coffee cup calorimeters is that we can consider these systems to be isobaric or they are at constant pressure because the only major pressure that is acting upon the calorimeter and its contents is the atmosphere, which is pretty much constant. So for this instance, let's say for example that a physical process is happening inside of our coffee cup calorimeter. Let's start with the basics. Let's assume that our process inside is the melting of ice and we want to know how much energy is involved in that process. So let's say for example, our calorimeter contains water at a certain temperature. Let's say, for example, the initial temperature of water is T sub W. And I want to know how much energy will it take for a cube of ice to melt. So I place a cube of ice in my cup of water in my coffee cup calorimeter. And the ice is initially at a temperature of T sub ice. Now, in this case, our system is the ice because we are interested how much energy will it take to melt the ice. Okay, so we will be designating the ice as our system and the water, which is around the ice, as our surroundings. So our coffee cup calorimeter here is an isolated system, meaning energies outside of the coffee cup calorimeter has little to no effect on what's happening inside. So basically what's happening inside is the warmer water is transferring its energy to the colder ice because the transfer of energy always happens from a high temperature to a low temperature. So let's begin with an energy balance. For an energy balance, we are just following the teachings of the first law of thermodynamics. To refresh your memory, the first law of thermodynamics states that the total energy going in should also be equal to the total energy going out of a process. Or another way of saying that is the energy that is being lost should always be equal to the energy that is being gained or that is being absorbed. So in our study of calorimetry, everything that is inside of the calorimeter would either lose or gain energy. Now, in our case, who will lose energy and who will gain energy? Energy is always being transferred from a higher temperature to a lower temperature. And since we are assuming that the water is warmer than the ice, that means that the ice is absorbing energy and water is releasing energy. The energy that is being released by the water is absorbed by the ice to allow the ice to melt. So we are saying that the energy lost by the water or the heat lost by the water should be equal to the energy gained by the ice. That is our energy balance if we are assuming that this is an ideal coffee cup calorimeter, because an ideal coffee cup calorimeter does not absorb or release energy. Okay? If our coffee cup calorimeter is not ideal, meaning it can also release or it can also absorb energy, in this case, our coffee cup calorimeter would almost always be at the same initial temperature as the water inside. So therefore, our coffee cup calorimeter is also losing energy because its temperature is being lowered. So we can also include the Q of the calorimeter as part of the components that are losing energy. That is another way for you to gauge which components are losing energy and which components are gaining energy. If the temperature decreases, that means that you are losing energy. If the temperature increases, then you are gaining energy. In our case, the ice is melting, meaning it's gaining energy in order for it to melt, and water is getting colder because of the ice, so it's losing energy. So this is our complete energy balance. Now, before we go any further, we need to discuss the two types of heat or the two types of heat that can be transferred. So if we denote heat as Q, we can classify that into two, the first being sensible heat and the second being latent heat. Now, the difference between these two types of heat boils down to, is there a change in temperature or is there a change in phase? When we say a change in phase, we are pertaining to the changes from solid to liquid or liquid to gas or gas to liquid or liquid to solid. So in our case, our system or the cube of ice, it's actually giving off its latent heat because it's changing phase from solid ice to liquid water. So if there's a change in phase, we call that latent heat. And by the way, if there's a change in phase, there is no change in temperature, meaning for latent heat, temperature is constant. So therefore, if our ice is at 0 degrees Celsius and it is melting, therefore the ice is staying at 0 degrees Celsius. The temperature of the ice will not change unless it melts completely, and by that time, it can then undergo sensible heat change. Sensible heat change is characterized by a change in temperature, whereas the phase is constant. An example of a sensible heat change in our example is the water in the coffee cup calorimeter. Because the water there is staying as a liquid, therefore its phase is constant. No, there is no change in phase, but it's changing its temperature. So from a higher temperature it's releasing energy towards the ice such that the temperature of the water gradually decreases. So the change in temperature means that there is sensible heat change involved in the water. Now, these two types of heats also differ in the way on how we calculate them. For sensible heat change, this is where you will be applying the equation Q is equal to mc delta T that I have introduced earlier. Remember, Q is equal to delta H for most of our processes or for most of our examples. Okay? You can see that this is really the equation for sensible heat because sensible heat is characterized by a change in temperature, and in our equation, the change in temperature is quantified as delta T. The delta T in this case is T final minus T initial, or the final temperature minus the initial temperature. Okay? Now for latent heat, since there is no change in temperature because temperature is constant and what's changing is the phase of the substance, our equation for latent heat does not contain temperature. So our equation is Q is equal to M times delta H of transition. So again, in this equation, M is the mass of the substance. In our example here, M is the mass of the cube of ice, and delta H of transition pertains to the enthalpy of the change in phase. So in our example, if ice or solid water melts to liquid water, that is from solid to liquid, the delta H of transformation is called the latent heat of fusion. Because the latent heat of fusion is involved in the changing from solid to liquid or from liquid to solid. If the change involves conversion from liquid to gas, let's say for example, if you are boiling water, we are transforming liquid water to gaseous water or to water vapor, the enthalpy change associated with that process is called the latent heat of evaporation because you are evaporating the substance from liquid to gas. The opposite, if you are condensing from gas to liquid, that is the latent heat of condensation. Okay? So please always remember the difference between sensible heat and latent heat. Also remember the formula that we will be using to calculate sensible and latent heat. So going back to our energy balance, let's take a look at all of our heat terms and then decide whether they are sensible heats or they are latent heats. Let's first take a look at Q calorimeter or the heat transfer associated with the calorimeter. Since our calorimeter is a solid, it's a styrofoam cup, and in the process, it's not changing its phase from solid to liquid or from solid to gas. There's no change in phase. However, there can be a change in temperature. Therefore, Q calorimeter is sensible heat. Next, let's take a look at Q sub W. So this is the heat associated with the liquid water inside of the calorimeter. The liquid water in this case is not transformed from liquid to solid or from liquid to gas. What happens is the temperature of the water simply goes down. So there is a change in temperature, there is no change in phase, therefore QW is also sensible. How about for the ice? In this example, our ice is supposed to melt because remember, our goal is to determine how much energy is involved in the melting of ice. So therefore, from solid water, we are transforming that to liquid water. There is a phase change, and when there is a phase change, there is no change in temperature. Therefore, Q ice is latent heat. So later on, if we will be solving such problems, for Q calorimeter and for Q water, we will be using our equation Q is equal to mCp delta T, while for Q ice, we will be using our equation Q is equal to M times delta H of transition. Okay? That's why it's very important for you to know how to discern between sensible heat and latent heat. Let's answer some examples. We add 3.358 kilojoules of heat to a calorimeter that contains 50 grams of water. The temperature of the water and the calorimeter, originally at 22.34 degrees Celsius, increases to 36.74 degrees Celsius. Calculate the heat capacity of the calorimeter in joules per degrees Celsius. And the specific heat of water is 4.184 joules per gram per degrees Celsius. So let me first draw the given. Okay, here are our given. So we have our calorimeter containing water. Since the water is always in contact with the calorimeter, it's very reasonable to expect that the temperature of water would be equal to the temperature of the calorimeter. In this case, both the initial and the final temperatures of the calorimeter and the water are the same. Initially, your water is at 22.34 degrees Celsius and your calorimeter is also initially at 22.34 degrees Celsius. And then it was stated on the problem that we are adding 3.358 kilojoules of heat to the calorimeter and to the water. So since we are adding heat and your system in this case is the calorimeter and the water, therefore the sign of Q is positive because this is heat that is being added to the system. And after adding heat to the system, we noticed that the temperature of the water and the temperature of the calorimeter rose to 36.74 degrees Celsius. So the temperature of water and the calorimeter increased, meaning that they gained energy. And if we will be asking how much energy did they gain, the water and the calorimeter combined gained 3.358 kilojoules of energy because as stated by the first law of thermodynamics, energy should always be conserved. So we are only introducing 3.358 kilojoules of energy. Therefore, the water and the calorimeter can only absorb 3.358 kilojoules of energy. Okay? Next, we write our energy balance. Our energy balance in this case would be Q that is added, or the amount of energy that is added, should be equal to the amount of energy that is being absorbed by the calorimeter and the water. And that is Q cal plus Q water. This should make sense because the amount of heat being absorbed is equal to the amount of heat that we are adding into the system. Okay? And in this case, our Q added is the 3.358 kilojoules of energy. We just have to convert this to joules. Later in our calculations. Now it's time to ask yourselves, is your QCal and QW sensible or latent heat? We see here that the calorimeter and the water have a change in temperature because the temperature varied from the initial of 22.34 to the final temperature of 36.74. So therefore, there's a change in temperature. There is no change in phase. Therefore, we say that QCal and QW are both sensible heat. And since they are both sensible heat, what equation are we going to use? We are going to use Q is equal to mCp delta T. Now, let us rewrite our energy balance. Our energy balance now becomes 3,358 joules. This is our heat added. I just converted it from kilojoules to joules by multiplying it with 1,000. That is equal to, for our Q calorimeter, that is the mass of the calorimeter times the Cp of the calorimeter times delta T of the calorimeter. Okay, again, mCp delta T plus mCp delta T of water. That's the mass of water, Cp of water times delta T of water. Now, in our case, as with many of our future cases, the water exhibits the same delta T as the calorimeter because they are in close contact with each other. So we can say that the delta T of water is equal to the delta T of the calorimeter. Next, take a look at your developed equation and then decide whether you have the given to solve this equation. Based on the problem, we want to know the heat capacity of the calorimeter. So in this case, we want to know the Cp of the calorimeter. However, if you take a look at our given, delta T calorimeter is given because that's the same as the delta T of water. The mass of water is given, that is 50 grams. And the Cp of water is given because that's a constant, that's 4.184 joules per gram per degrees Celsius. The problem is, we are not given the mass of the calorimeter. We're also not given the Cp of the calorimeter. In cases like this, we can modify our sensible heat equation to become Q is equal to S delta T, wherein the S is simply the product of the mass and the Cp. So with this change, we can now call Cp as the specific heat capacity, while the S is simply called the heat capacity. So do not confuse yourselves between the specific heat capacity and the heat capacity. The specific heat capacity has units of joules per gram per degree Celsius, that is energy per mass per temperature, while heat capacity has the units of joules per degrees Celsius. That is energy per temperature. So that's the difference between heat capacity and specific heat capacity. Although in some cases, the terms specific heat capacity and heat capacity are being used interchangeably. So it's up to you to recognize if the given quantity is specific heat or heat capacity based on its units. Okay, going back to our energy balance, the mass of the calorimeter times the specific heat capacity of the calorimeter can now be substituted as the heat capacity of the calorimeter. And we can now solve for the heat capacity of the calorimeter. Rearranging our equation gives 3358 joules minus mass of water, Cp of water, delta T of water, all over delta T of the calorimeter, and that is equal to the heat capacity of the calorimeter, S sub cal, S calorimeter. Let's substitute the given. So that is 3358 joules minus the mass of water is 50 grams. The Cp of water was given earlier, that is 4.184 joules per gram per degree Celsius. And the delta T of water is final temperature minus initial temperature. That is 36.74 minus 22.34 degrees Celsius. And that is all over delta T of the calorimeter. Now, the change in temperature of the calorimeter is the same as the change in temperature of water. So that should also be equal to 36.74 minus 22.34 degrees Celsius. Let's calculate. 3358 minus 50 times 4.184 times 36.74 minus 22.34 divided by 36.74 minus 22.34. So the heat capacity of our calorimeter is 23.99 joules per degrees Celsius. Final answer. Okay, that is how we solve calorimetry problems. You start with the given, analyze the given, and then construct your energy balance. Okay, that is how we apply the concepts of thermodynamics to calorimetry. So please watch out for a separate video detailing the solutions for sample problems starting from lesson 1 up to lesson 3. And that would serve as your reviewer for our first module exam. So please wait for that. That is all for this part of this lesson. I hope you have learned something. Please keep on honing your problem-solving skills. Thank you, and as always, keep safe.